The first rule is called the junction rule, and the second rule is called the loop rule. These are simple but very important rules that we need to learn when we analyze DC circuits. For the junction rule, it says summation of all currents at any junction is 0. By junction, we mean a point like this point, where 3 or more wires are connected. So imagine you have this situation, current is coming into this junction, and then at the junction it splits. Part goes this way and the other part goes this way. So all what this rule is saying is that the junction cannot hold charges of its own. Whatever comes in should go out. Usually we assign positive sign for the currents that are coming in and negative signs for the currents that are going out. So here I1 is coming into the junction, its sign is positive. I2 and I3 are going out of the junction, therefore they have negative sign. So I1 minus I2 minus I3 equals 0. It makes sense. This rule is very simple. It is, in a way, a statement of the conservation of charge. Charge cannot be created from nothing. Okay? Whatever charges come into this junction, they should leave that junction. The junction cannot store the charges, cannot generate charges of its own. Okay? The second rule says if you take any closed path, any closed loop, if you start at any one specific point and started to add the voltage difference across various elements in the loop, as you return back to the original point, the change in the voltage difference is 0. This is a statement of the conservation of energy. Okay, energy is conserved. Like in mechanics, if you start at the ground level, if you toss something up like a ball or a coin, and it returns back to the original point, the change in energy is 0. It's very much the same here. If you toss an electric charge in an electric field in any path and it returns back to the original point, the change in its potential energy is 0. Okay, so the first rule is an expression of charge conservation principle. The second rule is an expression of the energy conservation principle. These two rules are very important. I selected an example that we will be able to understand how to apply them. Now, for the conventions, when you build any circuit, as you to check on the voltage difference across various elements in a loop, you need to understand how to calculate the voltage difference, delta V. So here, if you have these 2 points and you are interested in the voltage difference between them, you have one of 2 possibilities. Either the current is going this way or the current is going that way. If the current is going this way from A to B, this means you are dealing with a potential. You are going from higher potential to lower potential. This is a potential drop. Because of that, we use a minus sign. On the other hand, if the current is going this way, so you are going from lower potential to higher potential, so this is a potential rise. Therefore, we have a positive sign. Consider these 2 additional graphs here. Okay, so for this is that these 2 graphs for resistors, these 2 graphs for batteries. So if you have a battery, A is the negative electrode and B is the positive electrode. So if you go from A to B, you are going from negative to positive. You will gain energy, you will gain potential. So it is a plus E. On the other hand, if the battery is flipped and A is the positive and B is the negative, then the voltage difference in this case between A and B is negative. It is minus E because you are going from higher potential to lower potential. Very simple but important convention that you need to understand in order to substitute the right sign as you apply the loop rule. Always, when you apply Kirchhoff rules to complex circuits, you need to label various parts of the circuits using proper symbols. You will assume certain directions for the currents. You will apply the junction rule to generate an equation. Then you apply the loop rule to generate other equations. Once you ended up with the proper set of algebraic equations, you solve them for the unknown quantities. Example: find the currents in the circuit shown here in the figure using Kirchhoff's rules. Okay, so here it's not easy. You cannot apply Ohm's law in order to solve for various currents. We need to apply Kirchhoff's rules. At the junction C here, when we apply the junction rule, we have I1 is coming to the junction, so it is positive. I2 and I3 out of the junction, they are negative. So you have I1 minus I2 minus I3 equals 0, or I1 is equal to I2 plus 3. Then let's select this closed loop, apply the loop rule. So for this loop, we have the voltage difference between the two ends of the battery plus the voltage difference across the 4 ohm plus the voltage difference across the 9 ohm. This is the full loop. We started at this point, B, then to C, then to D, then back to A, and from A to B. This is a closed loop. Now, in order to simplify, for the battery, we are going from negative to positive. We are moving this way clockwise. We are moving from A to B. So you have a potential rise. Therefore, it is positive plus 6 volt. Then for this resistor, the current is going clockwise. So we are dealing with a potential drop. So it is minus 4I1. And also for 9 ohm, the current going there is I3. So another potential drop, 9 ohm multiply I3. These are the only elements in the circuit. So this adds up to 0. Then we select the top loop here. And again, we apply the loop rule. For the 5 ohm, it is a potential drop. The current is going this way. So it's a potential drop. So it's minus 5I2. And for this one, it is a potential rise because we are going opposite to the current. So it's a plus 9I3 equals 0. Now we have 3 equations, 1, 2, 3, and we have 3 unknowns, I1, I2, and I3. We need to apply algebra to solve these 3 equations for the 3 unknowns. This is the first equation, I1 equals I2 plus I3. This is the second equation, 4I1 plus 9I3 equals 6. This is the third equation, minus 5I2 plus 9I3 equals 0. The physics part is done after generating these simultaneous equations. What remains is algebra. We need to solve these 3 simultaneous equations for the 3 unknowns. As you know from algebra, the number of simultaneous equations must be equal to the number of unknowns or higher in order to solve for the unknowns. So now we start with equation 3 and we solve for I2. The value that we will get it here, we will plug it into equation 1. So from this equation, I2 is 1.8 I3 when you simplify. So now we plug this in place of I2 here. So it's 1.8 I3 plus I3. This is 2.8 I3. Then we substitute this into equation 2 and solve for I3. So I1 is 2.8 I3, 2.8 I3. We put it here for I1. Okay, 2.83 multiplied by 4 plus 9 I3 equals 6. Therefore, I3 is 0.3 ampere. When we solve this equation with one unknown, I3 is 0.3 amperes. We go back now and solve for I2. I2 now, which is 1.8 I3, multiply 1.8 by 0.3, so it's 0.54 ampere. And we substitute in equation 2 to get I1. So I1 is 0.83 amperes. Okay, this is how we solve problems using Kirchhoff's rules. The assumption that we made for the direction of the currents in this loop and in that loop are correct because the result that we obtained are all positive. If we obtained a negative value for any one of these currents, then the negative value is just to tell us that the assumption that we made for the direction of the current needs to be reversed. Okay, so at the beginning, as we are assuming direction, we don't need to worry whether the direction that we assumed is the right one or not, because we know that at the end, if the direction we assumed is not correct, we will get a negative value for one or more of these currents.